Welcome to the slideshow on the Big Three Kinematic Equations. So we're just going to jump right in, and these are the Big Three equations that you need to know. And I encourage you to pause the video to copy these down somewhere and keep them in this order: Big Equation 1, Big Equation 2, Big Equation 3. One thing to note that wherever I use the S, which is displacement, if you saw the previous video which explained all the kinematic variables, S we could use delta X or delta Y instead of S if we wanted, and in many cases that's exactly what we're going to do. But for a generic equation, we're going to use the letter S because that is the generic variable for displacement. So, how are the equations similar and how are they different? There are 5 possible kinematic variables. And before you interrupt, I know the other video said that there were only 4, and the reason for that is the 5 variables are V, V naught, A, T, and S, but you see I color-coded them, and you see how there's 2 purple ones, the V and the V naught. Both initial velocity and final velocity I'm going to treat as separate variables for these equations. Now, each of the big 3 equations has exactly 4 variables. Each of the big 3 equations is missing 1 variable. That one cannot be part of your problem if you wish to use the equation. And acceleration is in every one of the big 3 equations. So let's analyze big equation 1. Big equation 1 says that the final velocity is equal to the initial velocity plus the product of acceleration and the time interval. So which variable is missing? The missing variable is displacement, which is S, or again, you can use delta X or delta Y. Therefore, if your problem involves displacement, you will not be able to use this equation. Okay, now let's analyze big equation 2. Big equation 2 says that displacement is equal to the initial velocity multiplied by time plus half of the acceleration multiplied by the square of the time interval. So what variable is missing? Just the final velocity. So if your problem has final velocity in it, you won't be able to use this equation. And also of interesting note is that big equation 2 is a quadratic equation with respect to time. Now let's look at big equation 3. In big equation 3, we have the final velocity squared is equal to the initial velocity squared plus 2 times acceleration times the displacement. So what's missing in this one? The time interval. Therefore, if your problem involves time, you won't be able to use big equation number 3. Interestingly, because of the quadratic nature of big equation 2, you might find yourself using big equation 3 as an intermediate, but we'll talk more about that in another slideshow. So, awesome. Let's take these equations out for a test drive. Example problem. Z is at a stoplight. His car is stopped, and he's distracted because he has his dinner in a bag in his lap. The light turns green, and he doesn't notice. The car behind him honks the horn, which startles Z. He stomps on the accelerator. In 6.41 seconds, he is going plus 26.8 meters per second, which is about 60 miles per hour. What is his acceleration? So the first thing I did here is I laid out the 5 possible variables, and we're going to identify what those 5 variables are, or actually we're going to identify what the problem tells us so we could eliminate the one that has nothing to do with the problem, and we can also see what the problem's asking us for. So the first thing, let's identify here, the question asks what is his acceleration, so that better be part of the problem. Our equation is going to have acceleration, but we already knew that because all 3 of the big 3 equations have acceleration in it. Next, we will know in 6.41 seconds, that is a time interval. So our problem is going to involve t. His car is stopped. Initially, his car is stopped because he's at a stoplight. That would be initial velocity, and this initial velocity is 0. Finally, we know that he finishes going plus 26.8 meters per second. So we have a final velocity, and therefore the odd one out must be displacement. Therefore, the equation that we're going to use cannot have displacement in it. So which equation has no displacement in it? Look at the equations that you had, and you'll find that it's big equation number 1. Big equation number 1 has no displacement in it. It says final velocity equals initial velocity plus acceleration times time. So let's relook at this problem to find our data. We know he starts, his initial velocity is 0, his final velocity is 26.8. We know time is 6.41, and we're looking for acceleration. Okay, so we're going to have to rearrange big equation number 1 to solve for acceleration. You should always take a moment to solve your equation in terms of the variable that you're looking for. So in this case, we're looking for acceleration. So I rearrange this by subtracting v0 from both sides and then dividing both sides by t, and you get a equals v minus v0 over t. Now again, this is our data. So what we're going to do is plug those numbers in, and we will get 26.8 meters per second minus 0 meters per second all over 6.41 seconds. And you will get 26.8 divided by 6.41, and you will get positive 4.18 meters per second squared. Now, I know that it says minus 0, and you might be thinking, well, there's only one significant figure in there. Well, 0 is infinitely significant. When we say at rest, you can say it's significant to as many zeros as you want it to be, 0.00000000, in which case we get 26.8 minus 0.0, and we'll still have 26.8, all three significant figures. So our final answer becomes plus 4.18 meters per second squared, and that should be evident from looking at the 26.8 meters per second divided by the 6.41 seconds. You'll get meters per second over seconds, which is meters per second squared. So let's try another problem. Yvette is sliding down a hill. She picks up speed at a rate of plus 1.56 meters per second. She started at rest, and it took her 4.92 seconds to get to the bottom of the hill. How long was the hill in meters? So again, here are 5 possible variables. The question is asking us for how long the hill was in meters, so it's asking us for a displacement. We also know the time interval is 4.92 seconds. We also know that she started at rest, which means that her initial velocity is 0, and her acceleration is 1.56 meters per second, right? So in this case, we don't have anything to do with final velocity, right? So since final velocity is not part of the problem, we need to find an equation that does not have final velocity as part of it. And when we look at all of our big 3 equations, we will see that this is big equation number 2. There's no final velocity in big equation number 2. Even better, so we're looking back at this data here, but even better, equation number 2 is already solved for us. See? S is equal to v0 times t plus 1/2 at squared. It is already solved for displacement, so now all we're going to do is just plug in the values. So we get 0 meters per second, right, times 4.92 seconds, plus 1/2 times the acceleration is plus 1.56 meters per second squared, multiplied by the square of the time interval, which is 4.92 seconds. So you square that. When you plug those numbers in and you do the operations, you will end up able to cross out that first term because anything multiplied by 0 automatically equals 0, so we're only concerned with the second term. And 1/2 times 1.56 times 4.92 squared, second squared, will end up canceling those second squareds out, and you end up with plus 18.9 meters. Now it's important that you leave that plus in there. I don't know why it's not colored blue, but don't worry about that. The plus indicates that the vector is in the positive direction. Remember, vectors have both a magnitude and a direction. So displacement, being a vector, says that it's 18.9 meters. That is the magnitude. That positive sign is the direction. So the final answer, correctly stated, would be positive 18.9 meters. It's also worth noting that the 1/2 in big equation 2 is infinitely significant, just like when we said 0 for at rest, and therefore does not impact your significant figures. Don't worry about using 0.5 as that and being like, oh no, I only have one sig fig. It's actually 0.500000, as many zeros as you need it to be. Okay, let's try one more problem. Xavier is jogging along at 2.49 meters per second. Suddenly he sees a mean bully up ahead and he quickly comes to a stop. If it only took him 1.64 meters to stop, what was his acceleration? So let's look at what we have here in this problem. Problem wants to find the acceleration, so A is definitely going to be part of the problem. V0, he initially starts off running at plus 2.49 meters per second. So we got an initial velocity. We also have 1.64 meters. It's positive 1.64 meters. That positive is implied, but positive 1.64 meters, so he skids to a stop. That is displacement. And stop right there, that is a final velocity indicating zero velocity. So therefore, time has nothing to do with this problem, and therefore we can ignore it. So, which equation has no time interval and has v, v0, a, and s in it? Hopefully you guessed it's big equation number 3, which says final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. Again, like in big equation number 2, that 2 is infinitely significant and is not going to impact your significant figures. It could be 2, 2.0, 2.0000000. It doesn't matter. It is infinitely significant. The next thing to do is rearrange big equation number 3 to solve for acceleration. Always, always, always do this. So what we're going to do is first we have to subtract v0 squared from both sides, and then we are going to divide both sides by 2s, and we get our final equation, which says acceleration is equal to v squared minus v0 squared, all of that over 2s. We then plug in these values. So again, to look at them again, we got the final velocity is a stop, so it's 0. Its initial velocity is 2.49 meters per second. We're solving for acceleration, and we know that it takes him 1.64 meters to come to a stop. So he's going to be slowing down. That's a key thing to pay attention to, because he's running and he comes to a stop. That means he's braking. He's coming to a stop. So let's plug these numbers in. We have v squared minus v0 squared. And if we put those numbers in, we will get 0 meters per second, that quantity squared, minus plus 2.49 meters per second, that quantity squared, all of that over 3.28 meters equals your acceleration. Again, remember, it's final velocity, the 0, minus the initial velocity. Well, final velocity squared minus initial velocity squared. So when you solve it, you will end up getting 0 minus 6.2 meters squared per second squared, all of that over 3.28 meters, which becomes negative 6.2 meters squared per second squared over 3.28 meters, and thus your final answer is going to be negative 1.89 meters per second squared. That makes sense because one of the meters cancels out, and acceleration should have meters per second, which is the same thing as saying meters per second squared. Okay, so to recap the big 3 equations, and yes, this is a bad pun here. That is a picture of Riptide from the Percy Jackson series. In case any of you are fans, you will know that Riptide will turn into a pen once you put the cap back on it. And the reason I have this picture on here is because originally I was looking for a nice play on the word recap, and I came across this disaster. It says disappointment. Noun, the feeling you get when an uncapped pen doesn't turn into a sword, which would be terribly clever except for the whole misspelling of the word disappointment, which left me disappointed. So to move on, there are 5 possible kinematic variables. The 5 variables are v, v0, a, t, and s, or delta x or delta y. Each of the big 3 equations has exactly 4 variables. Each of the big three equations is missing one variable, and that one cannot be part of your problem if you wish to use the equation. In any problem, sort out what you are given and what you are asked for. Sometimes the information is implied, such as "at rest" means 0 velocity. Always solve the correct big equation for the unknown variable before plugging in the values. Use the appropriate significant figures, identify directions on all vectors such as positive or negative, and label your units, and you will be done. Thank you for watching, and I'll see you next time.